Feedback describes a system in which the outputs of a system affect its inputs. Let's see what that means through an example. Here's a diagram showing our familiar object falling through air. This is the first time we're considering the forces on it as a way to explain its motion rather than just describing the motion. So we're using a dynamic rather than a kinematic treatment. Here's a constant weight downwards. It's only constant if we make a couple of assumptions, but they're reasonably valid. See if you can see what they are. And we're going to round G to 10 from 9.81 just to keep the numbers easier. And here's the upwards air resistance or drag force labelled D. We're going to assume that the buoyancy force on it is negligible, which will be reasonable if the density of the object is much greater than the density of the air through which it's falling. And then the key to this situation is that the drag D is velocity dependent. The faster the object, the quicker it has to expend energy displacing the air it's falling through, and the greater the force resisting the motion. As the object falls from rest, obviously it speeds up. The initial velocity is 0, and we want to know what happens to the velocity after that. So we'll explain that by making simple calculations at 3 points in the motion, and we'll do that for a 60 kilogram object, which could be a skydiver, for example. At the beginning of the motion, when there is no velocity, there's 600 newtons of weight, because it's a 60 kilogram object, and crucially no drag, because the drag depends on the velocity and there is no velocity. So how can we use those facts to describe the motion? Well, we use Newton's second law, which says that the resultant force, F, is equal to mass times acceleration. And the resultant force is the downwards weight minus the upwards drag. We can do the calculation for this stage of the motion. The resultant force is 600 for the weight, subtract no drag, and that has to equal 60 for the mass multiplied by the acceleration, giving an acceleration of 10 meters per second squared. So we can repeat this process now for an intermediate part of the motion where the object is already travelling. There's still 600 newtons of weight, but there's some drag now. Let's call it 100 newtons. The calculation is exactly the same, except that instead of no drag, there's now 100 newtons of drag. That reduces the resultant force to 500 newtons, and that reduces the acceleration to approximately 8 and a bit meters per second. Now eventually the drag is going to increase to the point where it balances the weight, and at that point there is no resultant force, so the acceleration is also 0. Doing the calculations at these 3 particular points makes it easier to understand the evolution throughout the whole journey. An increase in velocity causes an increase in the drag force, which causes a decrease in the resultant force, which causes a decrease in the acceleration, which causes a smaller increase than before in the velocity. This is a feedback loop. The drag depends on the velocity, but then the future velocity depends on the drag. So now we've looked at 3 numerical examples of the differential equation and explained the feedback loop in effect. Well, where is the differential equation then? Well, actually this is it. It's a differential equation in disguise. Well, the acceleration can be written as the rate of change of velocity. So the equation as a function of velocity is this. And this is a differential equation written as a function of velocity. And you could say that velocity and acceleration are both functions of displacement, so that we could rewrite the differential equation as a function of displacement, and you'd be right. And here it is. But we'll generally be using the first version throughout this section.